9? Yeah. We have Unit 9, Unit 10, and Unit 11. Actually, gases are in and of itself a unit that you'll see in chemistry, general chemistry, and you'll see in physical chemistry, but gases, not a lot is translated very often past this, but we're going to get into how molecules interact, okay? And that becomes very, very important, and energy transfers. Those are the kinds of concepts we'll look at the end of this. Some of the principles about how molecules interact are fundamental in how biology works. And so we're going to get back to the point of looking at a molecule and determining if it's nonpolar or polar. Oh my goodness, that meant I had to draw a Lewis structure and had to know if bonds were polar, but then had to know the whole shape. That is so fundamentally important to how things actually function in the real world. We very rarely look at one molecule. We always look at molecules interacting with one another. And so the fundamental concepts of it being polar or nonpolar translate and transcend why things happen in basically every class that you go on from here on in the sciences. So some of these fundamental concepts are going to be really, really important later. Now, gases tend to be well defined in terms of they're really not very difficult problems if, one, you could read the problem and identify what you have. That's always an issue when you do those kind of problems. And two, if you can divide and multiply and use a little bit of algebra in that, okay? And I'm going to show you some techniques that usually help you simplify the problem to as you get through it. You can do it other ways. It makes it more complicated. That means you can lose things as you do it. And so I want to try to show you a way to do it the most simply, okay, and the less manipulation so that you can get to a good and correct answer. And so when we talk about gases, okay, there was one overarching equation with gases. It's called the ideal gas law. Okay, what was the ideal gas equation? Do you remember?
PV.
Yeah, PIV NERT. Okay, PV equals nRT. What is pressure? What is P? And what unit is it? In what? The pressure units are always in values of atmospheres. Volumes are always in what?
Liters.
Liters. N represents what? Number of moles. And temperature is represented by what? Kelvin. The reason is R is a constant number, 0.08206. It has a unit of atmosphere times a liter divided by a mole times a Kelvin. And so if we use an equation, if we use an equation that uses R, everything must be in atmospheres, liters, moles, and Kelvin for this equation to work out. And so when you read an equation, what you're going to be identifying, or read not an equation but a problem, you're going to be identifying the things that you are given. Now last time we ended up with PV equals nRT, and the only thing we didn't solve for was R. Okay? And we didn't solve for R because it doesn't matter what conditions you have, okay? Things will adjust, the gas will adjust all of the different variables so that every time you multiply P times V divided by N times T, it will always equal the constant number, that's R. And so it wasn't very useful for us to solve R, although in lab, we're going to make you solve R experimentally. We're going to make you verify that R is really R if you do your problem right, okay, and your technique right. Okay, now what this does for us is it tells us that no matter what condition, if I take a amount of gas under certain conditions, and then I change something to a different condition, all the other three will change accordingly so that it will still equal R. So I can take the equation and say condition 1, condition 2, that's where the 1s and 2s come in, and make them equal to each other because R is a constant. Okay? Now, if I do some other things, if I make other things constant, like, okay, here's PV equals nRT, most of the time, all the time, R is constant, but most of the time in an experiment, we never change how much gas we have, the amount. So that is usually constant. And so if I solve for the constant things, then I get PV equals, or PV divided by T equals something that is constant. Okay? And so if I have a material, a gas, and I don't change the amount, and I don't change R, then I can have condition 1, condition 2, and this one is actually called the combined gas law. Okay? Where PV divided by T, condition 1, is equal to PV divided by T, condition 2. All right? If I make other things constant in RT, then if that's all constant, then PV equals PV. In actuality, who said there was a relationship between pressure and volume? Did anybody say that? Do you remember any of the peoples? Boyle. Boyle said if the pressure goes up, the volume goes down. This is a mathematical application of Boyle's law. Okay? Here, we're relating volume and temperature. Who related volume and temperature? Good old Chuck. Charles' law. Okay? This is a mathematical application of Charles' law. All right? And so we can make any value constant in this and then set the others equal to it, and then you have version 1, version 2. Now, here's the problem. How do I know when I use just Pivnert or do I use one of these? When you read the problem, you list what you have. That will lead you to what's going on. Now, in a problem, if by chance they don't mention something, then that meant that it didn't change, and so it's constant. So sometimes they will not mention something, and that is the assumption that nothing changed from condition 1 to condition 2. So if I read this problem here, okay, the gas pressure in an aerosol can is 1.5 atmospheres. All right, I have a pressure. It's 1.5 atmospheres. Okay, good. At 25 degrees, I have a temperature, 25 degrees Celsius. All right, and those two go together. Assuming that the gas inside obeys the ideal gas equation, what would be the pressure? It asks about a second pressure. So this becomes now number 2. This pressure is the first, and this temperature must be the first. I don't know what that is. What would the pressure be if the can were heated to 450 degrees? I have a second temperature, Celsius. All right, a couple things. Do I use the simple PV equals nRT? No, because I have condition 1s and condition 2s. But everything is derived from that. PV equals nRT. Now you could memorize every single condition 1, condition 2 equations. Okay? You can make a list of them and you can memorize them and you just fit them in. But here, what is constant? R is constant. What else is constant in this? Did they change the number of moles? Did the problem say number of moles have changed? Nope, that's the constant. Did it change temperature? Yes. Did it change volume? No. Okay, so what I'm going to do is I'm going to get all the constants together. That was constant. Okay. And I get now all the constants together. Okay. And I divide by T so that N, R, and V are constants, and I get P over T equals something that is constant. And so I get P1 T1 equals P2 T2. Okay? So I've made a relationship between temperature and pressure here. Okay. Now I could have memorized that that's how the relationship between how pressure and temperature work. Now, when I look at my equation, what am I actually solving for in my final problem? Which is it? The second pressure. I want this. This is a simplistic way to go about this. Do the math right here. Okay? So when I do this, I want to take temperature 2 times pressure 1 divided by temperature 1 equals the pressure 2. Okay? I've simplified. I don't have to move numbers around. I simplified for what I was solving for using the equation without numbers. All right, am I ready to plug things in? Can I do it right now? Why can't I just plug numbers in right this very second? The temperatures are what? In Celsius. What are the temperatures must be in? Kelvin. So how do I change Celsius to Kelvin? Oh my goodness, that's chapter, what, 1? Unit 1? Oh. How do you change Celsius to Kelvin? Add what? 273.15 plus 273.15. And so 289.15 Kelvin on the bottom, 1.5 atmospheres on the top, and, all right, 0.15, got that, 3, okay, 5 plus 7 is 2, carry the 1, 6 plus 2 is 7, plus another 1 is 723.15 Kelvin times 1.5 atmospheres divided by 289.15 Kelvin comes out to be, yep. Question? No, ask it.
You just said a number wrong, but you're good.
Did I?
Yeah.
298. My dyslexia is coming out, sorry. Yes, 298. So somebody put that in the calculator. No calculator?
3.638.
6.368, yes. 3.6, yeah. Now, looking at this, what is the sig figs? This is a bad sig fig question. 2. Because 25 is 2. What number is this one? Well, how many sig figs there? 2 or 3, but since we're doing multiplication, 2 is the smallest one that we can go to. Okay? All right. What did I do? I first, 1, identified what I had. 2, I determined what equation I needed. Okay? If it only had 1P, 1V, 1T, we could have used PV equals nRT and been done with it. But because it had condition 1, condition 2, I had to set the constant things together and put the variables, the ones that are changing, together. 3, I solved for the one I wanted before I put in any numbers. 4, I made sure all of my numbers were in the correct units. 5. I put every number in the right spot. 6. Make sure I put it in the calculator correctly. 7. Check sig figs. Okay? All right. First, identify what you had. Second, determine what equation you used. Third, solve that equation when it just has the variables there. Fourth, I made sure all my units were correct. Fifth, I substituted them in the right spots because it doesn't matter if you get them all in the right units. If you put them in the wrong spaces, you're going to get it wrong. And you can actually see in this, the units cancel out. It comes out to atmospheres, so the units will help you identify. 6, I put it in the calculator correctly, or someone did in the class. And 7, sig figs. Okay? And there's your answer. All right. First, what do? Identify what I have. Okay. An inflated balloon has a volume 6.0 liters. Great. At sea level with 1 atmosphere. Ooh, pressure. 1 atmosphere. And is allowed to ascend in altitude until the pressure is, pressure. If that is 1, then this is 1, then this is 2. And now I've gone to 0.45 atmospheres. During the ascent, the temperature of the gas falls from, I have a temperature, and at first it's at 22 degrees Celsius, and it goes to a temperature 2 of minus 21 degrees Celsius. Calculate the what? I don't know that one. Okay, listed everything. 2. Is this good enough? PV equals nRT? No. Which things are constant? R, good. And N. Then let's get all of the variables on one side, all of the constants on one side. Got it. So I'm going to use P1 V1 over T1 equals what? P2 V2 over T2. Okay. What am I solving for? V2. To solve for V2, multiply both sides by T2. Oh no, algebra. And then divide both sides by what? P2. So my equation will be, the answer T2 is, something's wrong. That should be P2, not T. Okay. My answer should be, oh shoot. Okay. I can erase. All right, P2. All right, so P2 times P1, is that correct? No. What in the world? Wait. All right, stop. Go back. I've done something bad. I can't do algebra. All right, where am I? Keep going back. Stop. Go back. Very slowly, it's going back. Every little line I made. Okay. Oh, how far back did it go? Oh, way too far. Oh, that's not good. I was a little overzealous. All right. P1 V1 over T1 equals P2 V2 over T2. Okay? Good. Times T2 on both sides. Okay? That gets rid of this. Divided by P2 on both sides. All right, that's good. Now, V2 equals the temperature 2, pressure 1, V1 over pressure 2 divided by T1. All right, very good. Whew. My next step, when I look back over at this, can I use these numbers? You have to convert, okay? So, oh, don't you even. Okay. 273.15. Okay, that is 295.15 Kelvin. 273.15. This becomes 252.15 Kelvin. All right, now I can use numbers. The temperature 252.15 times the pressure 1, which is 1, times the volume 1, which is 6, divided by, this is atmospheres, this is liters. Pressure 2.45 atmospheres, so atmospheres cancel out, times T1, 295.15 Kelvin. Kelvin cancels out, and I'm left with a unit of liters. All right. Someone do that. Ah. Okay, so what did you get? 11.39, and the number of sig figs I should use? 11 liters. I sure hope that's right. Yes. Woo. All right. All right. Now, I can do examples all day long, but what were the steps? Okay. The steps of this were to first what? Write down what you have. 2, determine an equation. 3, solve that equation when you have just variables. 4, go back and look and make sure all of your numbers in the correct units. 5, make sure the units go in the right spot. 6, put them in the calculator, right? Right? 7, sig figs. Okay? And so that stepwise process works for condition 1, condition 2 things, or it even works for PV equals nRT, because you'll only get much fewer variables. Okay? All right. New concept. PV equals nRT is great. And what I've done in this, I started with PV equals nRT, but I divided I manipulated it mathematically so that I put this on top, this on bottom. What are the units that I have right this very moment? For N is what? Moles. Over V is liters. This is as close as I can get to a density. What is density? Grams over liters, or mass over a volume. Okay? Now, in gases, density is grams per liters. What about liquids and solids? It's grams per what? What is the density of water? 1 gram per 1 milliliter. Solids and liquids have densities in grams per milliliters. Gases, though, have densities in grams per liter because there's so little material that you need a whole liter to get up to a number of grams. Now, manipulating the equation this way gives me moles over liter. It almost looks like density, but it isn't. But what can you do to moles? What can you convert moles into? Grams using what conversion factor? Molar mass. And so if N times the molar mass gives you grams, then if I can multiply both sides of the equation by the molar mass, then what happens is I can substitute N times molar mass on this side and just put grams. And on this side I get pressure times the molar mass divided by RT will give us a density. And it will give us a density in units of grams per liter. So if I have pressure and I have temperature and I know the molar mass, then I can calculate the density. And so I can rewrite this and say the density is equal to the pressure times the molar mass divided by R and T. This is a different equation. I showed you how we got there. You don't really have to know how you get there, although you should be able to, that shouldn't have confused you. But here's the deal. If you memorize this, you'll be able to solve one of the problems on the exam. I will ask you to solve a density, okay, of a gas, and I will give you pressure, molar mass, and temperature. Looking at this equation, what else could you solve for that is new? If you just rearrange this a little bit. What could you solve for that you couldn't have done before? If you do a little bit of algebra, you can get the molecular mass. Okay? That's just by doing a little bit. So, dirt divided by P gives you molar mass. Got it, see? The dirt divided by P. Okay, do you need to memorize both of these equations? Only if you can't do algebra. Okay? You can memorize 2 separate equations, one for density and one for molar mass, be done with it. Right? No thinking involved, just memorizing. Or you memorize one of them and then you can always solve for the other. Depends upon how much you want to memorize and depends on how much you want to think. Okay, that's, there's always an option. How much do I want to think? All right, and so I will make you solve a molar mass and a density on the exam. Okay, you'll have at least one of them, each of them. All right. Now, if you can find moles of the gas, then, oh my goodness, it can get to one of those big stoichiometry equations because if you go from moles of a gas, you can go to moles of anything else, and it's one more way to get into stoichiometry. You won't get away from it. It will forever haunt you. Ever. Forever. Okay. All right, new concept. Brand new concept. Dalton's law of partial pressure. Okay. This is a really weird concept. Remember when I talked to you about gases? Gases are moving so fast and are so far apart from each other that they behave like they're what? That they're all by them what? Themselves. They really don't tend to even notice that another atom or molecule is in the mix because of the speed at which they're moving. And they're just not close to anything. They're not interacting between the molecules. So if by chance you had a balloon inside of it, okay, and by chance the balloon has both nitrogen and oxygen in that balloon, all right, the nitrogen will make up part of the pressure in there. the oxygen will make up part of the pressure in there. The total pressure will be the sum of how much nitrogen is there and how much oxygen is there. And each individual pressure is determined separately, but the total is just the sum of the ones that are there. And whatever gases are in there, you just add them all up. In other words, the pressure total is equal to the sum of pressure 1 plus pressure 2 plus pressure 3 plus pressure 4, all the pressures of every gas that is there. Now, this is the reason why this becomes important. And when you do one of your experiments, this is where we have to account for it. If you're going to create a gas, how do you trap that gas? If you pour it into a test tube, that doesn't help because the gas will float right out. Okay? So we invert a beaker or a test tube over water. And see the bubbles being generated? That's the gas being generated. So the bubbles get trapped, and how do I know the volume? Well, I move this up and down to see, the volume is so much. Okay? But I have produced gas in there, but there's one more gas inside that container. So if you're producing oxygen and oxygen is bubbling in there, you've got oxygen in there. You got a lot of oxygen in there, but what else do you have? Okay? Well, you're collecting over water. Water evaporates. And so what you have is a little bitty, tiny bit of water pressure inside that volume that you have to account for. Now, water is kind of cool because we know at any temperature how much water pressure is coming off. So we can look on a table if we measure the temperature of the water. The temperature of the water will be exactly the temperature of the gas because it is cooled to that temperature. And if I know the temperature of the water, then I know the partial pressure of the water that goes into that volume. And so by measuring the water's temperature, I can get, and moving that beaker, I can get the volume of that gas, I can get the pressure of that gas and the pressure of water that's there, and I can get the temperature of that gas. That's a lot of things I can know about that gas. If I know the pressure, the volume, and the temperature, then I know how many moles are there because I can use the R value. And so we have to account for this pressure in this physical experiment. The pressure of the water plus the pressure of the gas that you produce. So this is where you'll fundamentally use it. Okay? But here is a problem that we might use. Okay? Now, here's the deal. Remember with limiting reagents, you had two different starting points? Well, when you talk about Dalton's law of partial pressure, you have two different things, and so they're treated separately, so that means you have to do a problem for each of them. I know, that's just ridiculous, but that's how it works. And so, if I take a look at this, okay, what do I have? A gaseous mixture, is made up of 6 grams of oxygen and 9 grams of methane, and it's placed, okay, well, let's just, I've got grams. Stop. I'm going to do oxygen first. I have grams of oxygen. That is 6.00. Then it says, I'm going to ignore methane right now. It says it's placed into a vessel that has a volume of 15.0 liters and is at a temperature of 0 degrees Celsius. What is the partial pressure? The pressure of this. All right, I have grams, volume, temperature, and pressure. All right, do I have the right units? No. Okay, in this case, I'm going to use PV equals nRT, and if I look at this, I have a temperature, yes. I have an R because I know that. I have a V and I have a P. What don't I have? N. What is N? Moles. I'm not given moles. But you're given grams of oxygen and I can convert what? grams of oxygen into moles of oxygen, because 1 mole of oxygen is what? 16.00 grams, as the CHEM-111 says. Okay? And so 6 divided by 16, I get point.
Wouldn't it be 32 grams?
32 grams. Yes, it would. Oh, here we go down the. I'm going to do one at a time this time. Okay, 32. You're right. That changes my whole thing. I would have had our big red box on CHEM-111, and that would have been very disappointing. Welcome to your life, huh? All right. Okay. So, what am I solving for? Pressure. N RT over V. All right. So, the pressure of the oxygen is equal to the number of moles, 0.875 moles, times R, which is 0.08206. I have a atmosphere in a liter divided by a mole and a Kelvin, times T, which is, 0. Do I put 0 in there? What would happen if I put 0 in there? Big red box, and the math would all work out to be what? 0. 273. All right, if you get a 0, that could be a correct answer, but you really need to check yourself. Could you have a 0 pressure? Yeah, there are really only strange ways you can do that. Okay. And divided by what? Volume, 15 liters. If I take a look at this, mole, mole, Kelvin, Kelvin, liter, liter, I'm left with atmospheres. Okay. And that times 0.08206 times 273.15 divided by 15, I get 0.280 atmospheres of oxygen. So I'm done, right? No. What have I left out? You got to do methane too. Exactly the same thing for methane. And then what is the answer? You add the pressure of oxygen and the pressure of methane to get the total pressure of the mixture, because that's what it wanted, the mixture.